So welcome back again. In the last lecture we have introduced splitting fields of a non-zero polynomial over a base field f, and we related the splitting field of the polynomial with a special kind of algebraic extension which we call the normal extension. And towards the end we mentioned a relation between the splitting field with polynomial and the normal extension. We mentioned, and I mentioned it as a homework, that if the extension is a finite extension, then it will be a normal extension if and only if the extension field is a splitting field of some polynomial over the base field f. So today we shall discuss another special kind of extension which we will call the separable extension. We'll also discuss some properties of finite fields. But before all that, let us define an algebraically closed field. Algebraically closed field. So a field f is said to be algebraically closed if every polynomial with coefficient in f has at least one root in f. So a field is said to be algebraically closed if whenever you take a polynomial over the field, then that field must have at least one root in that field itself. In general, you have seen that by Kroneker's theorem, that whenever you take a polynomial from a given field, we can always construct an extension, a bigger field, where the polynomial has at least one root. It may not always be true that a root will always lie in the same field. For example, so number one easy example is Q, R are not algebraically closed. Because we have seen polynomials. For example, for e.g. this x square plus 1, this is a polynomial over qx, and hence this is also a polynomial over rx, has no roots in R and hence in Q. So if you are asked Q is not algebraically closed, then x square plus 1 is a polynomial over Q which has no root in Q. Similarly, R is also not algebraically closed because this is a polynomial over R, but both the roots are complex, they are not in R. On the other hand, by fundamental theorem of algebra, so this is a result which we will not prove it here. This can be proved taking help from analysis only. Without analysis, purely from algebra, we cannot give a proof of this theorem. What this theorem tells, that C is algebraically closed. That means any polynomial over complex numbers will always have roots in the complex field itself. You do not have to extend the field. So the complex field is algebraically closed, but the rational field and the real field They are not algebraically closed. So for another example is a finite field can never be algebraically closed. No finite field can ever be algebraically closed. This is because let f is a finite field, so let us f equal to a1, a2 up to an. So f will have finitely many elements. So what we have to show? Our job is to construct a polynomial which has no root inside f. Okay? Then your fx, if I define a polynomial like x minus a1, x minus a2 up to x minus an, plus I take the 0 element, or you can say this is my a where a belongs to f and a is not equal to 0. So since I have taken f equal to a1, a2 like that, so that means 0 is also some of the elements here. 1 is also some of the elements here, because a field must have 0 and 1. So here I have taken all the elements one by one, x minus a1, x minus a2 like this. But the last term I should write anything, I can write 1 also. I want to write an element which can be any of the elements from f except the 0 element. So I could have written here 0 equal to a1, 1 equal to a2 and so on, because 0 and 1 must be there. Then I could have written here 1. Then I have no need to write all these things, because I have also written 1 here. So that means here it is a2. So what is that? Then you see, then clearly E is a polynomial over f. Why is a polynomial over f? Because all the coefficients, if I multiply this polynomial out, all the coefficients will be some product and sum of the elements a1, a2. But since it is a field, sum and product of elements of a1, a2 are again in the field f. So this is a polynomial whose coefficients are in f. What can you say about the roots? Note that for any I, what can you say about f of ai? F of ai is ai minus a1, ai minus a2. At one term I will also get ai minus ai, because I have written all the elements here. So the last term is again ai minus an, then plus 1. So see, this factor, since ai minus ai is coming, this will be 0, but plus 1 is also coming, so this is 1. And in the field, you know, this can never be 0. 1 and 0 are never equal in a field. So what I have seen, that no element of the field can be a root of this polynomial, because if I put any element ai of the field, I get 1, which is non-zero. Thus fx has no 0 in f. So algebraically closed field means what? Whatever polynomial you take with coefficients in that field, then this polynomial must have at least one root inside the field itself. But we are able to construct a polynomial which has no root inside f, but the coefficients of the polynomial are in f. So it is enough for us to conclude that f is not algebraically closed. So f can't be algebraically closed. So one of the important things, a field, note, a field is algebraically closed one equivalent one way of saying this is if and only if every irreducible polynomial over f is linear. That means since all the roots, you see, since all the roots lies in the field itself, so f is algebraically closed, means actually we can go further and say that if it has one root in the field, then by applying induction we can actually show that a field is algebraically closed if and only if all the roots lies in that field. So I can write here, note that a field is algebraically closed if any polynomial over f splits in f itself. Any algebraically, if field f is algebraically closed if and only if any polynomial over f split in f itself. So generally by Kroneker's theorem we know that every polynomial over a field has a splitting field, but that splitting field may be bigger than the original field. But if the field is algebraically closed, not only any polynomial will have one root, we can actually show that any polynomial you take, it should have all the roots inside the field. So it is not a difficult deduction to make, that from one root you can actually go on to say that all the roots must lie inside the field itself. So this is again equivalent to showing that a field is algebraically closed means every irreducible polynomial over f must be linear. Because why? Because you see, any polynomial, since any polynomial splits in f, so I can write any polynomial as some constant times x minus a1, x minus a2, x minus an, etc. Because these are all linear, splits into linear factors. So linear means what? You see, any quadratic or any cubic, it breaks up into linear factors. So here only irreducible polynomial can be linear only. So note 2, R is not algebraically closed as seen above. We have already argued that it is not algebraically closed. However, we can check that any irreducible polynomial over R is either linear or quadratic. So you check it here. It is not difficult to check that. Here in over complex numbers, since it is algebraically closed, any irreducible polynomial over a complex number must be linear because it is algebraically closed. But since R is not algebraically closed, so irreducible polynomials need not be linear here. But the situation is not much worse. We can show that any irreducible polynomial over real field is either linear or quadratic. You see, linear polynomials are always irreducible because we have defined irreducible polynomials in such a way that any 1 degree polynomial is irreducible. So linear polynomials anyway will be irreducible over any field, not only in R or C, but over C, these are the only irreducible polynomials. But over R, quadratic polynomials can also be irreducible. So using the fact that any odd degree polynomial with real coefficient always has at least one real root. Existence of real root is equivalent to showing that that polynomial is irreducible, because we can divide by x minus a whenever a is a root. So try to argue that any polynomial over R is irreducible if and only if it is either a linear polynomial or a irreducible quadratic polynomial. You can use here the fact that complex field is algebraically closed. That means any irreducible polynomial over the complex field is always linear. That fact you can use. So try to deduce this. So next, let us try to move to this separable polynomial. Separable polynomial. Our main interest is to define separable extension, but let us begin with separable polynomial. Okay, let f be any field and fx be any polynomial over f. We say that fx is separable if fx has no repeated roots, repeated or multiple roots in its splitting field. Because you see, the roots may not be inside f, but we are guaranteed to find all the roots in the splitting field of the polynomial over f. Because in the splitting field, the polynomial breaks into linear factors. So all the roots are guaranteed to be found in the splitting field of the polynomial. So a polynomial is separable means what? All roots are unequal. It has no repeated roots. If all roots of a polynomial are unequal, we say that the polynomial is a separable polynomial. Okay, so let us try to define separable extension. Separable extension. Having known what is a separable polynomial, we can use the idea to define separable extension. So let k over f be an algebraic extension. Just like in the definition of normal extensions, we require the extension to be algebraic. Here also we are beginning with an algebraic extension. So as soon as you have an algebraic extension, then every a belongs to k is algebraic over f, and therefore we can talk of its minimal polynomial. Its minimal polynomial mu a fx. This is a polynomial over fx. We say that a is separable. So first we have defined a polynomial to be separable. Now an element is separable over f if mu a fx, its minimal polynomial. If an element is separable means what? Its minimal polynomial is separable. Polynomial. So we already know what is a separable polynomial. There is a polynomial whose roots are distinct. Now an element is said to be separable if its minimal polynomial is separable. So we say that a field extension kf is separable if every A belongs to K is separable. So separable extension means what? Every element of the bigger field should be separable over the smaller field. But what is meant by an element is separable? By an element is separable means its minimal polynomial is separable. But what is the meaning of an polynomial is separable? A polynomial is separable means it should not have distinct root. It should have distinct root in its splitting field or anywhere actually. A polynomial, if you know all the roots and if you can check that all the roots are distinct, no two of the roots are equal, then we can say that the polynomial is separable. Okay, so let me mention some quick important results. So there is no time actually to prove all these results, so I will mention the important results. If you are interested and motivated enough, you should find the proofs in any standard textbooks. You are always welcome to see the books, and if you have any difficulty, feel free to consult me over phone or WhatsApp. So any extension, any algebraic extension of a field of characteristic 0 is separable. That means, that is, if characteristic of f, the base field, is 0, then any algebraic extension k over f is separable. So if the characteristic of the base field is 0, then any algebraic extension is separable. So there is nothing more to be checked. Then what happens? In characteristic P, if characteristic of f equal to P, then a polynomial fx belongs to fx is separable when what will happen when fx is a polynomial in x to the power p. So in general, fx is a polynomial in the variable p, but if the polynomial takes a special form, that whenever the variable occurs, it occurs only in powers of p, That means, for example, you see, fx is not separable. Here it is not separable only when fx is a polynomial in xp. For example, for e.g. This x square minus 2 belongs to z2x is not separable. Why? It is not separable. Why? Because here the characteristics of the field z2 is 2, and here whenever x occurs, only one time x is appearing, and it is appearing as a power of x square. But x cube minus 2 is separable over z2, because here this is x cube is not a power of x square. Here characteristic is 2, but this x cube is not a power of x square. So it is a separable polynomial. The only way a polynomial may fail to be separable over a characteristic p field is that the polynomial is a polynomial in the variable xp, not only it is a variable in x, it is a polynomial in xp also. That means whenever x appears, it appears as x to the power p, x to the power twice p, x to the power thrice p, and so on. So once you have a look at the proof, you should be able to understand. Okay. So an inseparable extension, when you want to construct an inseparable extension, then you should not look at characteristic 0 fields. Because if the base field has characteristic 0, then this extension will be always separable. So if you want to construct inseparable or non-separable field extension, then you have to consider the base field whose characteristics is not 0. You have to consider base fields whose characteristics are prime, maybe Z2, Z3, Z5, and so on. Okay, so you can try to construct inseparable field extension. You should try to construct a field extension which is not separable. So just have a look at this. So let us now move to the section finite fields. So finite fields, in the beginning of field extension we have mentioned something, that the power of a finite field must be power of a prime. The order of a finite field must be power of a prime. There is no field with whose order is not a power of prime. So this we have already proved. If f is a finite field, then what happens? Then order of f must be equal to power of some prime, where p is a prime and n is a positive integer. Then only we will get some fields, finite fields. We have also shown that, seen that if p is prime and n greater than 0, there exists a field with pn elements. Namely, how we constructed this field? We constructed this field by Zp. We have whatever prime is given, we will construct the field Zp, construct the polynomial ring, then construct the quotient ring Fx. What is this Fx? Where Fx is an irreducible polynomial. Irreducible polynomial of degree n over Zp. So we have shown that this gives rise to a field whose order is exactly p to the power n. But there is a problem with this construction. The problem is that it is not easy. There is no such algorithm which allows us to construct an irreducible polynomial of degree n over Zp. Over Q we can construct irreducible polynomial by using Eisenstein's criterion or mod p reducibility test and the rational root test, like that. But over Zp there is no such test which allows us to immediately construct irreducible polynomial of degree n. So it is theoretically this Zpx by ideal Fx always is a field with p to the power n elements, but practically it is difficult. If I want you to construct a field with 5 to the power 7 elements, suppose I want you to construct a field with 5 to the power 7 elements, then what you have to do? You have to take this field. This part is not difficult. This part is not difficult. But you have to write something here, a polynomial of degree 7, something like this. But it should be irreducible over Zp. But there is no such way to check whether a 7-degree polynomial is irreducible over Z5. So this way, even though it is theoretically okay, but it is difficult to check. So we shall try to give a new way to construct existence of field with Pn elements. So that is what we will see. We'll construct a field with p to the power n elements, which is we can do in our practical lives, which is not as difficult as what we have seen in the earlier process. So let us try to do this. First, recall that any finite field should have characteristic P for some prime P, and in that case we have seen that F can be considered as an extension of ZP. So this much we have seen in the beginning of field extension. So any field of characteristic P is an extension of ZP. So so what we will do, P is given to us, N is given to us. Okay, so consider the field ZP. So this field is known to us. You consider ZP equal to, what is this field? This field is nothing but 0, 1 up to P minus 1. So this is the field of equivalence classes modulo the prime P. So this field is known to us, but this is the field with P elements. But what we need is a field with P to the power n elements. So what we will do now, we will construct a polynomial. So define or let fx. So this is a polynomial x to the power p to the power n minus x. So this is a polynomial of degree n. These coefficients are what? 1 and minus 1, and these are elements of ZPX. This 1 and minus 1 is nothing but P minus 1, this equivalence class P minus 1. So this is a polynomial over any field, because 1 and minus 1 will be there in any field. So this is also a polynomial over this. So what we know now from field extension, so every polynomial has a splitting field. So let K be the splitting field. K be the splitting field of this polynomial. Over which field? Over ZP. Okay. So what is the splitting field? It is the field obtained by adjoining to ZP all the roots of this polynomial. Okay. So this is what is. So first what we will do, also what we will do, let F be the set of all distinct roots of this polynomial fx, where is these must lie in K, because all the roots of the polynomial fx must lie in the splitting field, but the splitting field may contain other elements, but we are only considering the set of roots of this polynomial inside K. There is no root outside K. All the roots are inside K because K is the splitting field. What is the splitting field? It is the smallest field where this polynomial can be written as a product of linear factors. Since it is a product of linear factors, the coefficient must be lying inside the field K, and so all the roots of this polynomial must lie inside K. So what is K? Here there are three fields we are considering. First, given the prime P, we are able to construct the field ZP. Now what we have assumed K? Since we know that every polynomial over any field has a splitting field, so this polynomial fx will also have a splitting field over the field Zp. So this we have assumed as K. So starting from the field Zp, we have another field K. Then we have construct a subset of K. What is the subset? In the splitting field, what is there? K is the splitting field, means K is the smallest field containing the original field Zp along with the roots. Now I have collected all the roots of the polynomial inside the set and I have named this set as f. Let us see what are all the roots. Then you see, then clearly what we can say, cardinality of f cannot be what? P to the power n. Because we have seen that over a field, a polynomial cannot have more roots than the degree of the polynomial. Here the degree of the polynomial is p to the power n. So the number of roots of this polynomial anywhere, all the roots we know in the splitting field is there, but outside K also the number of roots cannot exceed the degree. Here degree is p to the power n. So the number of elements in f cannot be more than p to the power n. It may be less. Why? Because some of the roots may be repeated. This polynomial has exactly p to the power n roots in K. If we allow repetition, if we count an element, a root, as many times as it is repeated, then the number of roots will be exactly p to the power n. When it will be less? It will be less when some of the roots are repeated. But here you see, moreover, can some of the roots be repeated here? Moreover, what is the derivative of f dash x? So there is a concept of formal derivative in a field. You see, since this is over a field, this is a polynomial over a field, we are not in real analysis. So there in real analysis all the polynomials are over R. So we can take derivative. A polynomial is a function. In real analysis, if you can consider a polynomial as a function, so we can take derivative. But here we are not in a field. A field has no limit or analytic structure. It has only algebraic structure. So we cannot take derivative in a field. But there is a concept called formal derivative. Formal derivative means without knowing anything about limits and all those things, given a polynomial fx, suppose a0 plus a1x plus a2x square, given a polynomial like this, we can define the derivative to be what? As exactly as in case of real analysis. Suppose we define this term, we define this. Is this again a polynomial? Given a polynomial this is again a polynomial. So we define this polynomial to be the derivative of this polynomial without knowing anything about limit and all those things. We will pretend as if this is happening in real analysis. Whatever the formula comes out, we will write. This makes sense in a field because this is also a polynomial, because if there are finitely many terms here also there will be finitely many terms, and these coefficients here it should be from the field f. These are also from f. Whenever a0 is there, here there is no a0. Whenever a1 is there in the field, a1 is there. Whenever a2 is there, twice a2 will also be there in the field, because twice a2 is nothing but a2 plus a2. So if we apply that concept in this polynomial, so what will be the derivative of this polynomial? It will be p to the power n x p to the power n minus 1 minus 1. So this will be the formal derivative of this polynomial. But you see, we are in a field of characteristic p. We are in a field, this you see, this Zp, this is a polynomial over Zp. What is the characteristic of Zp? It is p. Characteristic is p. So what is the meaning of characteristic is P? P into anything. P into anything. P to the power, here it is P to the power n. So if I write P to the power n minus 1 into x p to the power n minus 1. So this is an element where this is in Zp. Zp or what? Zpx. This is in Zpx minus 1. Now this is in Zpx. The characteristic of Zp is P. So characteristic of Zpx is also P. A ring and its polynomial ring, they have the same characteristic. So a ring has characteristic P means what? Characteristic of R is P means what? Px. If you add any time any element xp times, you get 0. So this means actually this element is added p times. But whatever be this element, if I add p times, I should get 0. So 0 minus 1. So this is minus 1. And in a field, this is not 0. In a field, minus 1 can never be 0. Now you recall that a polynomial can have repeated root. A multiple root means what? That root must be a root of the derivative. For example, you see if fx is x minus 2 whole square, if this root is repeated, then if I find f dash x, then this 2 will also be a root of f dash x because this is 2x minus 2. So a polynomial can have repeated root only when the root also is a root of the derivative. But here derivative of the polynomial fx is a constant minus 1 which can never be 0. So this is a constant polynomial having no roots. No roots. So it is impossible that f and f dash can have common roots because f dash x has no root at all. So what can we consider? So fx and f dash x cannot have a common root. So fx cannot have multiple roots in K or anywhere. So what can we conclude? So what is the order of f? Order of f is p to the power n. Because we have seen earlier that the number of roots is p to the power n counting multiplicities, counting the repetitions. But there are no repetitions. All the roots are distinct. Cannot have multiple roots means what? All the roots are distinct. So exactly how many distinct roots are there? Equal the degree of the polynomial, which is p to the power n. So we were actually looking for a field with p to the power elements. But what we have achieved so far is a set whose number of elements is p to the power n. So if you can somehow show that f is a field, then you are done. Because in that case f will be a field with p to the power n elements. So now what much we know? Does f is a subset of K, because f is the set of all the roots of the field K, subset of K with Pn elements. So we have to show that f is a subfield of K. If we can show that f is a subfield of K, then f itself will be a field. And how many elements f has? P to the power n. So now let a comma b belongs to f be any elements. So subfield means what? Whenever a and b are there, a plus b, a minus b, ab inverse, everything should be there in f. Now what is the meaning of ab belongs to f? What is f? F is the set of roots. So then a comma b are roots of what? Roots of fx. What is fx? xpn minus 1 in K. So what do we know about AB? They are elements in K. What kind of elements? They satisfy this polynomial. So a to the power p to the power n equal to a, b to the power p to the power n equal to b. Because a is a root of fx means f of a equal to 0. That means a to the power p to the power n minus a equal to 0. So a to the power p to the power n equal to a. Similarly, b to the power p to the power n is b. Now what we have to show, that if these equations are satisfied, then a plus b is a root. What is the meaning of that? A plus b is a root. Then I can show that a plus b is a root means if I put here p to the power n, then I should get a plus b only. But you see, since the characteristic is p, so by binomial theorem what we know, this is nothing but a to the power this. Why it is so? Since characteristic of Zp is p. Whenever the characteristic is p, these are elements of actually k. So characteristic of k equal to characteristic of Zp equal to p. Why these two characteristics are equal? Because we have seen that whenever kf is a field extension, then these characteristics are same. Why? Because when I have a subfield, when f is a subfield of k, the identities of f and k must be the same. The multiplicative identities must be the same. And the characteristics of a field only depends on the identity. It is the least positive integer such that n1 equal to 0. But the 1 in k and f are the same. So the value must be the same in f and k. So since this k is an extension of Zp, and we know that characteristic of Zp is p, so the characteristic of k must also be p. And so if I raise this to the power n, all the middle terms will become 0, only this will remain. But a to the power pn equal to a, b to the power pn equal to p. So if I write a plus b pn, I get a plus b. If I write a minus b to the power pn, I get a minus b. So what does it mean? This implies a plus minus b belongs to f. Why? F is the set of all the roots. So here a plus minus b also satisfies this polynomial x to the power pn equal to x. So this is also there in f. What can you say about this? ABPN, what is this? Since a field is a commutative operation, multiplication, so I can write this as APN, BPN. But this is AB. A to the power Pn is A, B to the power N is A. So this means AB is also a root. So AB belongs to F. Finally, what about A inverse? A inverse Pn. This is nothing but A Pn inverse. So this is A inverse. So this implies A inverse also belongs to F. Okay? Hence, F is a subfield of K with Pn elements. Okay? So, F must be a field with Pn elements. So, if you give me a field with, if you give me a prime number P and if you give me a positive integer n, I can give you a field with Pn elements. How is this field constructed? It is constructed as a set of all the roots of a specific polynomial. What is the specific polynomial? X to the power p to the power n minus x. This is considered as a polynomial over Zp. Then we take the splitting field of this polynomial and we take the collection of the roots of this polynomial. That turns out to be a field with p to the power n elements. Okay, so this is how we show or construct a field with p to the power n elements. Okay, now it is also a fact that, so next observation is, so next theorem is what? Any polynomial any polynomial with p to the power n elements must be a splitting field, of x to the power p to the power n minus x over zpx. So try to understand the statement of this theorem. First, you have given me a prime number p and a positive integer n, and you asked me to construct a field with p to the power n elements. So how I have given? I have constructed the polynomial x to the power pn minus x. Then I have constructed the polynomial, the splitting field, and I have shown that this f, the field with p to the power n elements, is a splitting field of this polynomial. Then the question may come that is it the only way to construct a p to the power n elements? So this theorem says that yes, whenever you have a field with pn elements, in whatever way you construct this field, ultimately it has to be a splitting field of the polynomial x to the power pn minus x. So once we can prove this theorem, since we have mentioned that splitting field of a polynomial over a field is unique up to isomorphism, so we can say that any two finite fields of order p to the power n, they are also isomorphic. Why? Because this theorem says that any finite field, it must be a splitting field of the same polynomial x to the power pn minus x. But we know that any two splitting fields are isomorphic. So whatever way you construct your fields with p to the power n elements, they must be isomorphic to one another. So it means that there is only one finite field with p to the power n elements. Any field with p to the power n element is uniquely determined up to isomorphism. Okay, so I'll skip this proof. You try to check that proof in any book. Okay, yeah. Next, let me see the group structure. Of finite fields. So here I'll mention two results. The proof I will briefly indicate. You can check in any standard book. What it says: the additive group of a field with pn elements, p to the power n elements, is isomorphic to Zp cross Zp direct sum up to Zp with n summands. N summands means what? The number of summands will depend on the power. This prime p, Zp here is coming. How many times it will come? It will come exactly the power times. If it is p square element field, 2 copies of Zp. If it is p cube, then Zp plus Zp. Why is it so? This is an application of, so it is an application of structure theorem of finite abelian groups. So you should be familiar with the structure theorem of finite abelian groups. So what you have to only show, since I have a finite field. So under multiplication also F star forms a group, but since F is a field, this group is an abelian group. So the additive group of a finite field is a finite abelian group. So by structure theorem, it must be direct sum of cyclic groups. Direct sum of cyclic groups. But there are many ways to write the direct sum. It will depend, we need extra information to check which option is there. For example, you see, if it is Z, it is P cube, then I can write ZP cube as ZP plus ZP plus ZP. I can also write ZP square plus ZP. I can also write as ZP plus ZP square. But which one should I write? It will depend on the fact that any element, the order of any element in the additive group of a field is the same P. So what I am trying to show is that, note that if X belongs to F is any non-identity or non-zero element, then order of the element X is P for all X where belongs to F. F star, yeah, 0 I am excluding, F star in the group F plus. In the additive group, so I should write F0 not equal to F. In the additive group, 0 is also there, and order of the 0 element is always 1 in any group, so it cannot be P. Order of the identity is always 1. But other than the identity element, whatever element you take, its order in the additive group F plus is always the same prime P. It cannot be anything other than P. Why is it so? Because you see, if I write, if order of this X is equal to M for some M greater than 1, then you see, then since Px equal to 0, why Px equal to 0? Because this field F has characteristic P. This field has characteristic P. So Px, any element X you take, you add it P times, it will be 0. So you see, order of X is equal to M in F plus means what? Mx equal to 0. And M is the least integer for which this happens. But P is any other integer for which also Px equal to 0. So what must happen? So we must have, since M is the least integer, we must have M divides P. Since order of Ox equal to M, this means what? Mx equal to 0. X added M times equal to 0. Because what is in a multiplicative group, what is the meaning of order of A equal to N? This means A to the power N equal to identity. So if we multiply A N times, I get the identity. So if the notation is additive group, so that means this multiplication power will become multiple, because I have to, in place of multiply, I have to add. If I add A N times, I should get NA, and I should get the identity. Identity means here additive notation identity is 0. So I should get NA equal to 0. So if order of X equal to M in an additive group, that means M times X is equal to 0. But by virtue of the fact that the characteristics of the field F is P, the characteristic of the field is P. Why characteristic is P? Because order of the field is taken to be P to the power N. So that prime P must be the characteristic of the field. So Px is also 0. But m is the smallest such integer because order is defined to be the smallest integer for which m times x is 0. So this m must divide P. But since P is prime, so what must happen? So either m equal to 1 or m equal to P. But m equal to 1 implies what? Order of x is equal to 1 means what? X must be the identity element. Identity means 0 here. Because identity is the only element whose order is 1. Okay? So, if x is not equal to 0, that means what? M must be P. So, x is not equal to 0 implies M must be equal to P. So, whenever x is a non-zero element, then its order M must be equal to P. So, in a finite field, whatever non-zero element you take, its additive order is the same. And what is the additive order? It is P. So in that case, by structure theorem, the only decomposition of Zp to the power n is this. It is a n copies of the field Zp. So this is how the additive group structure is. And for multiplicative group, it is a very standard result you will get in any book. The multiplicative group of any finite field is cyclic group. So this is a very common result in field theory. So what it says, the finite in a finite field, the multiplicative group must be a cyclic group. So this proof I will not do. You can check in any standard book. So let me now come towards the last result of this course, which is the subfield structure. The subfield structure of finite fields. So what it says, let F be a field with Pn elements. Then F will have a subfield. F will have a subfield with P to the power m elements. Obviously m will be smaller than n because the subfield means fewer elements. So if this m divide n. So this result says that all subfields of a field with P to the power n elements is P to the power m elements for some smaller values of m. What kind of smaller values are allowed? Only those values of m are allowed for which m divide n. So if I take a field with 81 elements, so 81 is 3 to the power 4. If I ask you whether this field has a subfield with 27 elements, 27 is 3 to the power cube. So can a field with 81 elements have a subfield with 27 elements? The answer is no by this result. Why? Subfield is possible only when this power divides this bigger power. Here the smaller power is 3, this 3. Bigger power is 4, but 3 does not divide 4. So this field with 81 element cannot have a subgroup with 3 cube 27 elements. So in that way this result helps. The proof should not be difficult. First assume that first assume that F has a subfield. F has a subfield E with Pm elements. Then we have the tower. We have the tower of fields. Which tower of fields? Any field with characteristic P is a subfield of Zp. So F has P to the power n elements, this has P to the power m elements, and this has P elements. Also, this, what is the degree of Zp? E over Zp. This is a field with P to the power m elements. So its dimension, this is equal to dimension of E over Zp. So this is nothing but m, because this has P to the power m elements. And similarly this F over Zp, since this has P to the power n elements, so this will be n. Now by multiplicative property of degrees, what will happen? This F over Zp is equal to F over E. This is E over Zp. So this is equal to n. This is equal to m times Fe. M times Fe. So from this you see that n is a multiple of m. So this implies m divides n. So if a field with P to the power n elements has a subfield with P to the power m elements, then this m must divide n. So this is a very important result. So conversely what we have to presume, we can assume, conversely assume that m divides n. So what we have to prove? We have to prove that any field with Fn P to the power n elements will have a subfield of P to the power m elements. So since any field with P to the power k elements, k can be anything, is a splitting field, this much we have proved. If any polynomial, any field with pk elements is a splitting field, of what polynomial? Of the polynomial xpk minus x over which field? Zp. So it suffices to show that xpm minus x divides xpn minus x in Zpx. So why it suffices to prove this? Because the roots of this polynomial are the elements of the field with P to the power m elements. So here the roots of the polynomial are the elements of the field with P to the power n elements. So if I can show that this divides this, that means any element of this will be an element of this. That means any element of the field with P to the power m elements will be a element of the field with P to the power n elements. That means the field with P to the power m elements will be a subfield of the field with P to the power n elements. That is what we require. Okay. So you have to show that this happens. What is given to us? We are only given that given that m is n, m divides n. So from this you have to prove this. So you see, step by step you go. See here mn is there. Next first step is this mn. Then n equal to what? M into k for some k. Okay. Then P to the power n minus 1, I can write as what? P to the power mk minus 1. So this is p to the power m whole to the power k minus 1. So this I can write as what? As a geometric series like this. If you know this formula, it is better. Pm plus p twice m plus p thrice m up to p k minus 1 m. This is the geometric series. Pm twice m this. What is the sum of this series? You see, this sum is what? This sum is p to the power m to the power k minus 1 divided by p to the power m minus 1. So see, why this formula is equal to this? If this is equal to this, if I cross multiply this with this element, I should get this element. So here see, this element is this element. So this is equal to this into this element. Okay? So I do not have to write this. So from this, what can you say? From this we can say that p to the power m minus 1 divides p to the power m minus 1. So this is an important step. So I can write again this p to the power n minus 1 equal to some r into p to the power m minus 1. Okay. So now you see, now this x to the power p to the power n minus 1. You see this p to the power n minus 1, then minus 1 again is equal to what? From here, x to the power r p to the power m minus 1 minus 1, because p to the power n minus 1 is equal to r into p to the power m minus 1. So again, if I use the same formula, x to the power p to the power m minus 1, so this is r minus 1. So if I use the same formula here again, x to the power pm minus 1 minus m, then 1 plus x to the power p to the power m minus 1 plus something like this. So from this, what it says, x to the power p to the power m minus 1 minus m should divide x to the power p to the power n minus 1 minus 1, because this is a multiple of this. Now to get the result, what we need, I have to multiply both sides by x. If I multiply both sides by x, I will get this. So this is what we require. So this shows that once I can prove this, this shows that this x to the power, so any root of x to the power pm minus 1 x is a root of x to the power pn minus x, because this is equal to this into something. So whatever roots this polynomial has, these are also root of this polynomial. So this polynomial may have some other roots, but anything of there must be there. So this is the same thing as saying f p to the power m is a subset of f p to the power m, because any element of fpn is a root of this, and any element of this is a root of this. So this fpm is a subfield of this, because both are fields. fpm and fpn both are fields, one is contained in the other, so this is a subfield of this. So this implies fpm is a subfield of fpn. So by fpn, this is a standard symbol, f written like this. It is a symbol used to denote the field with p to the power n elements. We have proven that given any p prime p and any positive integer n, there is a unique field with p to the power n elements. So that field is denoted by f p to the power n. So whenever m divides n, fpm is a subfield of fpn, and conversely. Okay, so all the subfields of a field with finite fields, it corresponds to the divisors of n. The number of divisors and number of subfields will be the same. So with this, let me stop today's video and this will also conclude my course on algebra 2. I would have loved to do some more results, or I would have loved to complete all the proofs, but due to lack of time and this online thing, it is not possible to do all these things. So I wish you all the best, and I hope you will do well in the exam. So I'll not be uploading any more lectures for this course. If you have any doubt in any of the course, you can WhatsApp me or you can call me anytime. So thank you again for your cooperation. Thanks.